Sounds like we have a disagreement. Go ahead, let's chat about it. What's going to happen to the variance? As I take more data, what do I expect to happen to the variance of the mean? We're talking about variance of the sample mean, okay? Not of the data, but of the sample mean. As I get more and more n, more and more data, do I expect more variance or less variance? Go ahead, have at it. Okay, so what is the mean number of heads here? What should x bar be? What do we expect x bar to be? 0.5, right? How much of the time are we close to that 0.5? Let me put close in perspective, okay? Right now, I might be 0.5 above, or I might be 0.5 below. Every single time, I will be 0.5 above or 0.5 below on one coin toss. I can't be any closer than that. Okay, let's move on to this one. Okay, what is x bar supposed to be? It should be 0.5. Some of the time, I'm actually getting that 0.5 now, right? But still, half of the time, I'm 0.5 off this way or 0.5 off that way. But still, half of the time, I'm right on. So is my variance bigger or smaller? I've actually got some data points in the right place now. Smaller. Right? I've got smaller variance now. Because it used to be that every single time I was off by 0.5. Every single time. Now I'm only off half of the time. Okay? Now let's move on to this one. Here's my x bar at 1/2. That's what I expect it really to be. That's what the expected value of the mean is. Okay? Now I'm off by 1/3, 3/8 of the time, and I'm off by 1/3, 3/8 of the time. But how many times am I off by a whole half? Actually, that's not even 1/3, right? Sorry, I'm really good at fractions. 1/6 off. How often am I off by a full 1/2?
Well, half of the time.
Only half of the, no, not half of the time, because this is 1 out of 8. That's 1 out of 8. I'm glad you guys are as good as fractions as I am. Okay, 1/8 of 1/8 is? A quarter. So I'm only out that far a quarter of the time. It's the same, you're right, it's the same width every time, but what's happening is I get more and more data. I'm getting more and more inside. The probability, see this one, the probability of me being at 1/2 away is fairly constant, right? As I get here, it's more likely that I'm getting data in the middle. As I get here, it's even lower on the outside, right? Because all of these should have the same area, because they should all add up to 1. So the more data I take, the more samples I take, the more narrow this becomes, because it's more likely that I'm actually going to be getting averages in the middle. What would it look like if I did 4 coin tosses? Right? I'd have a very small probability of getting no heads, a very small probability of getting, and that would be what, 1 out of 16? And this would be 1 out of 16, so very small probability of getting 4 heads or no heads. Okay, slightly better to get 2 of each. And then even better, sorry, one heads, 3 tails, 3 heads, 1 tails, and then pretty good to get 2 and 2, because now there's a lot of different ways to get 2 and 2, right? So it's getting even more centralized, which means what about the variance?
Smaller.
Variance is even smaller. Are you convinced yet?
Yes.
Okay, I'm going to do a little more, just because I can. We already made the statement that we believe that our data will become a normal distribution for a sample mean, right? Actually, I should erase that, but so here is the normal distribution of x bar. So this is actually the mean of x bar, because this whole graph is x bar. So this is the average value. So expected value of x bar is that number right there. I take one data point. Is it going to be right on that line?
Probably not.
Probably not. In fact, I have a fairly good probability of it being somewhere within that first standard deviation, maybe right there. Okay, so let's say it's on the edge, just for simplicity's sake, of that first standard deviation, which means, you know, there's, what was it, 65, so 35 probability of it being in that. What's that? 68. 68, sorry. I was just giving rough numbers, but yeah, 68. We should use whole number, it's fine, it's still a whole number. But anyway, right, about 2/3 probability of being in that area. What's the probability that it's going to be on the left side again? What's the probability that I'm going to get a number that's lower than the mean again? Half of the time, right? Okay, what's the probability that I'm going to get something lower than this point? Because I got 68 between here, right?
60.
Which means there's only 16% probability that I'm going to get it further to the left, that I'm going to be drawing my average away from the middle. Most of the time, 84% of the time, my point is going to be over here, which is going to bring this, my mean, closer to the middle, right? The more points that you have, the more likely that you're going to be closer to the middle. So once again, by adding more points, the variance of our sample means is going to decrease. Okay? Because I added another point. Say I added this one. So now my value is here. Again, is it more likely to be to the left or more likely to be to the right? It's more likely to be to the right, which means this is going to move to the right. Now, as soon as I pass the mean, it's now more likely that my next point is going to be on the left-hand side, which means it's going to move back and forth until, with enough points, it should be really close to the sample mean. So, again, the idea is the more points I get, the smaller my variance is. And this leads us to the second part of what we're going to do with the sample mean theorem, which really, this is the sample mean theorem. What we're going to do is kind of a corollary or something that comes from that idea, is that the variance, so we said central limit theorem, as n gets large, the sample mean approaches a normal distribution, which means that we expect the sample mean to be equal to the average of either the population or the sample, because those are the same thing, right? Because we said that that's a good estimator for this. Okay, so we expect that to be that value. However, there will be some variance. And so the variance of x bar is going to be equal to the variance over n. Okay, so this is the variance for one data point. How much can that one data point vary? Every time I add another point, it's going to slightly decrease. Okay? Now, obviously, going from 1 point to 2 points causes a big change in variance, right? But as soon as I get up to many, many points, it's going to cause less and less change in that variance, right? Have you heard of the law of diminishing returns? Yeah? Economics, right? Economics. The more data you take, the less it actually changes your results. Okay? At the beginning, one data point is not worth anything, right? Once you get 5 or 6 data points, we've definitely narrowed our variance. Now, depending on how accurate we need to be, depending on the data, you may want 100 data points, you may want 1,000 data points, but recognizing that as I get up to bigger numbers, the variance isn't going to change very much anymore. Okay? Now, if your variance starts off very large, then maybe it's still worth it. But if your variance starts off small, then maybe you don't need that much data points. Which is why a lot of the times in our chemistry and physics, in our labs, we say, you know what, 5 to 10 data points is enough, because after that, the variance isn't really going to be affected that much for the data that we're collecting with the accuracy that we're getting. Cool? All right.